internal networks. And then there's a whole other set of classes that are reserved for other purposes. So if you hear of RFC 1918 addresses or private IP addresses, that's what it's referring to as this class of reserved IP addresses for internal use. For IPv6, they moved to 128-bit addresses, and those are represented by groups of hexadecimal numbers, pairs of hexadecimal numbers, separated by colons. There's a whole nomenclature scheme where you can have two colons next to each other to represent a whole bunch of zeros, but won't get too much into that. Even though it is over a decade old, adoption has been rather slow. There are even major networks that haven't at all implemented them. Or if they have, the adoption hasn't been very fast at all. But if you do run into an IP address and it's a big long string with colons, that's what we're talking. Sorry about that. So an IP address in binary, it's like that. And it translates over to what we more typically see, which are the decimal separated periods. And there's a couple of things that you need to make sure you know, is that even for every subnet, there are reserved IP addresses. So a subnet is a chunk of IP space that you're able to describe using what's called a subnet mask. And that has to go into some binary arithmetic to be able to compute what the significant bits are. We won't go into that, but the important bits are to identify the parts of your subnet. The first address here, as the example here, is 192.168.123.0/24. That /24 is a 24-bit subnet mask. This is what's called CIDR notation. Up until that /24, that's the IP address that defines the subnet. So this is the very first one. And for most intents and purposes, you can't use it. And then the very last one, in this case, because it is a /24 subnet masked subnet, that last IP ends with the 255. That is what's called the default broadcast address. If you send a packet with that address, it will actually be replicated and sent to everyone. There's some good and some bad with that. There are additional ways of doing broadcast and multicast, but we won't get into those. So this also breaks down a bit more that you can't use all of the IPs, okay? We have the network being defined by that first one. If the network also is linked to other networks, you will need an IP address assigned to be able to send traffic to that other network. That's often referred to as a gateway. And so you'll need at least one IP address assigned to that gateway. For a lot of the Class Cs, that's how you're gonna see it. It's just with one gateway. But do know that it is possible to have more than one. And then we have to go into routing. We won't delve into that today. If you have a standalone network, however, that's not linked to any others, you don't have to have a gateway. And so you have one more IP address to use. And as I referred to earlier, there are a number of subnets in the IPv4 world that are reserved. those top three are your private IP addresses that are RFC 1918 space. And then you have a whole class A, which is there's another way of divvying up subnets and describing them: class A, B, and C. Class C is what you're more commonly going to run into. That's that /24. A class A is a /8, and that just means a much bigger chunk of IP space. And then that /16, that's a class B. It's a little bit smaller, about half. But then there are also additional reserved networks for all sorts of specific purposes. One example is on number 5 here. This /10 is for carrier grade NAT, network address translation. I've only seen it used a couple of times. But again, don't use that space unless it's your own private little network that never talks to anything ever. If you're connected to anything else and you use that special set of IP addresses, some routers will identify them, know what's going on, and not route it properly. If you want a full list of all of the reserved subnets, we have a URL there, and I believe the slides will be available.
Yes.
Yes.
After.
Yes. So now I'd like to talk about the two most common protocols for getting application data from one point to the other, and that's TCP and UDP. TCP came first, and its primary focus was on making sure that that packet of data successfully goes from the source destination to the destination. It has a number of built-in algorithms for ensuring that actually that delivery happens, or if it doesn't, that hopefully both sides will know about it, but at least the destination will know about it so that it can request a retransmit. UDP, on the other hand, doesn't have any of these safeguards built in and relies on the application itself, if it cares about a particular stream of data, to handle those retransmissions or counts packets to make sure it received everything. So an example here for TCP is that first connection, the first part of the connection is, do you want a glass of water? And the destination says, yes, I would like it. Okay, here's a glass of water. And the destination says, thanks for the glass of water. And then, was the glass of water good? And destination, yeah, that glass of water was good. And that destination again says, please give me, apparently very thirsty. For UDP, however, it's just simply, here's a glass of water, and we'll literally let go, and if the destination's not there to pick it up, it will fall on the floor. And UDP doesn't care. And in fact, we'll just continue to hand glasses of water out, whether or not they're picked up. So you can actually take this and use it to your advantage in some situations where you wish to not actually send data to anything, but have it picked up by like a network intrusion detection system. Sometimes we use UDP streams out to IP addresses that don't exist, just to throw packets onto the network so you can see them. UDP is primarily used for transmission where every packet isn't super important, like audio and visual communications. If you accidentally drop a few packets on the floor, you just get that little jitter or a little spark in the audio stream. And it really doesn't matter. You can still understand what's being said and see what's on the video screen. So this goes in a little bit further to describe a lot of the things I already talked about. The TCP is going to guarantees actually kind of a strong word. It tries its utmost to make sure that that packet gets there and that it knows that it got that, the destination got that packet, so it doesn't have to resend it. It can work together with ICMP for even doing some congestion avoidance. That can actually cause some additional problems. But it is an awful lot of overhead in that protocol. On top of the data that's going, all of the checksums to make sure that everything was transmitted and received correctly, the counts of the packets, where it is in the sequence, plus some security measures, makes the TCP somewhat bloated. There's a lot of overhead there. UDP has the advantage of not having any of those, so the packets are much smaller. However, you lose out on a lot of those built-in features. And if you care, again, about the data that comes for each packet, you've got to do that in your application. Or more likely get an application that cares and does it for you. I'm not sure how many developers are in the room. So some of the protocols that use TCP, you might notice have also been around for quite some time. So SMTP in email, IMAP, as well as POP, all of that uses TCP by default. You could finagle it around and get it to use UDP if you really wanted to. Web browsing primarily still uses TCP, though there's a new protocol called Quick that can use either, and at least the way it's being implemented by a lot of the big vendors like Google, it's using UDP. FTP and SSH are real heavy TCP. I've not seen the implementation of either of those that use So this is what a TCP header looks like. We've got the source port and destination, the sequence number and acknowledgement number, the header length, a reserved block that's used sometimes, but most often not. And then the TCP flags. These are primarily how it tells what's supposed to be in this packet and where it is in the sequence of the handshake that initiates the connection, the back and forth getting the data to this destination from the source, and then finally tearing that connection down, preferably gracefully, but some applications aren't graceful. The window size has to do with how many packets are going to be put together and how big the data set is, and then a whole set of TCP options. And this is all before you get to the data. So you can see there's an awful lot of overhead here. Before we talk about traceroute, I want to show you Wireshark. How many people have worked with Wireshark? No. All right. Great. I'm not going to be showing you anything new, never. Especially since get this big enough. It's just really not wanting to be.
It's there.
What's that?
A lot of digits.
There is a lot going on. A couple of bumps, but it's good news. Is that at all viewable? All right,
Yes.
all right, great. Okay, so a protocol that we haven't talked about yet, but is rather crucial is ARP. And this is kind of this bridge between that layer 2 and layer 3. It primarily is used, as you can see here, for devices on the same network to ask where another device is. So in this case, the device that has 192.168.123.1, which by the way is the gateway on our demo network. It's asking the network, because you might notice the destination there is broadcast. What is the MAC address, or in this case, it's saying it as who has the 192.168.123.100, which is, if you remember, one of the honeypots.